so apparently we are recording. So it is about multiplicative. Let's see how visible this is. Let me know if I can maybe zoom in. This is maybe better. So multiplicative. Okay, this marker is not good, so I'll switch to the next one. Multiplicative coalescent. And multiplicative coalescent is something that I was born with mathematically, academically, research-wise, because it was a topic of my thesis. And then for a long time, I was not doing any multiplicative coalescence, but I was studying other coalescents alone or with collaborators. And then some years ago, I came back to the topic. And now Vitaly is collaborating with me on a related topic. Yes, so hopefully he can tell you about this at some point. So I'm turning off my camera because, so let me see, it's this. Okay, so now you have only the screen with the writing. Okay, so there is a very much related discrete model called Erdős-Rényi random graph, and so binomial model. And sometimes it is just called Erdős-Rényi random graph. And it is usually denoted by GNP, and it is a mean field model. So there is no geographical space, mean field. You just have n vertices. That's the first parameter. And P is a value between 0 and 1. Okay. It could be 0, it could be 1, but then it's not interesting. So P is a probability. And it is kind of a homogeneous, well, stochastic homogeneous graph. It looks the same from every vertex because what happens, so P is a probability that this edge ij, so for any I and any j in the n, okay, so this is the set of, I give to each vertex a label, okay? We give a label. Label can be 1, 2, up to n, and this set is a set of two elements, undirected edge, so it's like an undirected directed edge, and it is open in, okay, it is open, so edges can be open or closed, or they can exist, it exists or does not exist with probability P for every pair, you know, for every I different than J. So there is n choose two at most n choose two edges, n choose two edges possible. But they're on the average, so expected number of open edges is of course P times n choose 2, right? I forgot to say, and so this is happening independently. So ij, so edges are open, being open is independent.
Could you please move it
Yes. Thank you. Being open is independent over different pairs. Okay, let me try something. Let me try to lift this. Okay, it will be better. It may be better, but then I have to, so I had to work on this instead of trying to chat. Maybe now it's better. So it is almost my sheet of paper. Okay, maybe like this. Okay. And now just slightly like this, or like, okay, no. Yeah, sometimes we spend time fixing this camera in advance, but okay, like that. It will be much better. So now, okay, so this is the model, and I hope that you've seen this already. If you haven't, it's okay. It's typically people draw then these n edges. I mean, sorry, n vertices. So 1, 2, and so on. So this is a very small image, and because it's not so important for what I'm going to say. I will draw another one, which will be better. And then maybe some edges, here's your P, and with probability P, some edges are open. So green is open. And others do not exist. They are not open. And then you don't see them. There is white line between them. Okay? And so this has existed since the 70s, maybe earlier. So in a famous paper by Erdos and Reni, they studied this model, the random graph, actually a different model. So this is called binomial model because it's already changed from the original one. They had, just for historical to be correct, so Erdos-Renyi random graph was you take n vertices and then one by one, uniformly at random, you pick a pair and then you add edge between them. So it was some kind of a dynamic way of adding uniform edges between pairs of vertices. And they already had an evolving model, and that's what I'm going to also look at. But this is an easier model for many. So they're kind of equivalent. Whatever you can prove about Erdos-Renyi original model, you can translate into a statement about the binomial model very easily. And over time, people prefer to look at the binomial model. So this is our page 1, and I move on to page 2. And okay, so here's the thing. Since the 70s, many things became known. So this was very famous. I mean, starting from the work of Erdos and Reni, became instantaneously famous. And the reason is that they discovered, so it's kind of the basic model for phase transition. So phase transition, and in fact phase transitions. So they may have looked at connectivity. So if you have a graph, you ask when is it connected or not. That's a natural property. But today we will look at most of the time at another phase transition that is also very important for Erdos-Renyi random graph, and that is the existence of the giant components. So there is something called the giant component, and informally it is a connected component of size order n. Okay, remember there are n vertices, and so here by connected, I just mean, of course, path connected, right? And we say that I and j are connected by path. So this is event, in words you would say I and j are connected by a path. In the graph, in this random graph, this just means that there exists, ik, some finite path such that I equals I1, j equals, say, in, no, not n, m. Okay, so k goes from 1 to m, and then all of these edges, I1, I2 is open. So it's an intersection such that, okay, such that all of them are open. I1, I2, I2, I3 is open, and so on. You keep going up to IM minus 1, IM is open. Okay? And having a giant component just means, okay, so connected component is the largest sort of largest connected subgraph of this random graph, or of any graph. But you know, here the graph depends, so it's omega by omega that you are checking this. You're checking, you know, for how many connected components there are and what size they are. You can arrange them, these sizes, so you could put, so that's what we are going to do soon. So we will look at connected component sizes. And what do I mean by that? Well, of course, if you have a connected component, then you can count its vertices. So the size is number of vertices inside of a connected component. Okay, so a giant component would be something that takes over almost all of the graph. The graph might not be connected at that point. You could have isolated vertices, you could have small components which are on the side, but somehow you might have a giant. And what Erdos and Reini discovered in their famous paper in the 70s is that there is a critical scale. So so they said, okay, so there is P, if you say P, Pn, okay, Pn of C. So this is a function of C. So I have n is my number of vertices in the graph, and here's a function that is good for this property. So I'm just taking a C and dividing by n. So it turns out that, so this is, there are three phases. There is phase transition for the giant component. Hello? Vous voulez...
Normalement, il va faire ça ici, c'est pour ça
oui,
qu'il est en train.
Oui, oui, mais je suis en train de parler...
Ah, d'accord.
OK.
Ah, d'accord. C'est pour la poubelle.
OK. OK, sorry about that. So I was... there is a phase transition for the giant component in the sense that if you now take, let's call it x1 is the number of vertices of the largest, and if they are ties, then you take, you know, one of the largest connected component. Then it turns out that there is three regimes. So C could be less than 1, C could be 1, or C could be bigger than 1. And you are looking at this as n goes to infinity. So that's, you know, always there is some asymptotic, it's asymptotic property. So the size of our graph is getting bigger. There's more and more vertices. And however, these connected, so this is P. So we are looking at G, N, P, and C, in fact. You could look at G and P, but it turns out that already at these very small connected probabilities, probabilities of connection of edges, so open edges, there is something interesting happening. And so if C is less than 1, so these probabilities are going to 0 at order lower, I mean, in this way, lower than 1 over n, then x1 is of order log n with high probability. So let me not be precise here. So this means, well, you can state it in terms of, you know, okay, there is NEM models, so maybe you can define them all on the same probability space. But I hope you're understanding this in some very natural way. So the events that x1 is between two constants, multiples of log n, these events have very high probability, higher and higher probability as n goes to infinity. Now, if c equals 1, then it turns out that x1 is of the order, again, I'm using theta, or I could use, so it's of order, there is a funny n to the 2/3, so power, and then even x2, this is the second largest. So there is the largest, there is the second largest, and even the kth largest. So maybe Erdős and Renyi didn't understand all of that, but maybe they just studied the largest. But it turns out that later on, probabilistic combinatorists or combinatorial probabilists understood that no matter how many components you go down, so some finite number of components, even the kth largest component is also of the order n to the 2/3. And all of that you can state, you know, formally and rigorously with high probability. And then when c is bigger than 1, then x1 is of order n. And x2 is of order log n. So, yes. So the connected, I mean, being open is still very small probability, but c is bigger than 1. And so with this, it is sufficient so that so this is, you know, around c equals 1. Well, just after that, the giant component appears. So this is, you know, giant is born. Giant is born. And the others are very small, and soon they will join the giant. They somehow, you know, if you keep going with, if you keep increasing the probability of being open, they will join very soon. And okay, and so here, this is the critical regime. So they discovered this is critical regime. And in this critical regime, you don't see a giant, but you see something that is, well, of the order n to the 2/3. And you see many components which are about equally large. And then they, you know, they need just a little bit. So these k and more components, just a little bit more to merge together and form the giant. Okay, so this was one of the first, this was before percolation. In fact, this is kind of a percolation model without space. Percolation, but without spatial structure. And so it is kind of a prototype of these mean field. It's a random graph without structure. And there is still this phase transition and many others that happen even in this model, and they have been studied through the years and decades. And so in the 1990s, when I was in graduate school, so mid-90s, just before came out a paper which was celebrating this work and adding more the work of Erdős and Rényi and adding more and more, kind of state-of-the-art combinatorial probabilistic results about the critical regime, maybe other regimes also. And then my former thesis advisor got interested in this work and tried to find a probabilistic. So these were, more or less just combinatorists who knew a lot of probability theory. So David Aldous is truly a probabilist, and he got interested in the critical regime, and he had his own very famous work that I was the first reader of that work, and so later on it became something. I'll tell you maybe what was the result of my thesis, but maybe not, because then I won't get into the immigration. So he was, I think his work was published either 96 or 97. And he understood something, here's a kind of a key property, first key property of the model. Let's change time. So a time change. But okay, before that, so I already mentioned percolation. So it is clear that you can realize on the same probability space. So you have G and P. So let's call this, graph GP, so random graph, which is distributed according to G and P. And so you can clearly construct all of them together on the same probability space. So you have some omega fp, so that if P1 is less or equal to P2, then they are as graphs. So graph has its vertices, but n is fixed, okay? N is fixed, so P is a variable here. GP1 will be a subgraph of GP2. I hope that this is clear. Okay, I could just say you could use, just like in percolation studies, you could, for each pair of vertices, you could use a uniform random variable. So you could have a uniform on 0, 1, and you could simply look at the events that Uij is less or equal to P. These are binomial, so, well, it's not the event, but the indicator of Uij less or equal to P. That's a binomial 0P. Bernoulli, sorry, Bernoulli P. Bernoulli P, that's what I was going to had to say. It's not a binomial. So Bernoulli P. And they are coupled in a good way. So of course you can use this Bernoulli P for the for checking or setting when the edge ij is open within G and P, and then you just need to use, as P grows, it is clear that Uij less or equal to P1 will be a subset of Uij less or equal to P2. And so if you are using, this will define your coupling, and this coupling will have this property. And in fact, this is good because then you can, think about an evolution. So there is a dynamic. So this is dynamics. It's very similar to what Erdős and Rényi had in mind in their work when they studied their own model. So you have a graph that starts from a completely a trivial, totally disconnected random graph. It's not random because P is 0, so this is at P equals 0. there is no open edge, and then as you raise p, as you increase the p, the edges start appearing and evolves to completely, totally connected to the connected graph. Usually it's called Kn, right? At p equals 1. So this is okay, a good way of looking at random graph model, and then even better way, according to Aldous, was to start putting in exponentials, so that instead of, so this is the time change. You have a new parameter q, and q is a number in 0 infinity. It's a real number, and so your p is now 1 minus e to the minus q, and there is a good reason for that, so that uij less or equal to p. So in the above coupling, in the above coupling, you have this event. These are the main events for checking openness of edges. But now this becomes, okay, I'm, correct me if I'm wrong. It becomes something like minus log 1 minus uij less or equal to q. And then, of course, you can check it directly or indirectly. In any case, this is a new random variable eij, and it has exponential. It must have exponential distribution with rate 1. Okay, so it is an exponential rate 1 random variable. It's seen from here. Probability that this is less or equal to q is p, which is that. And so now we have a graph, a random graph, an evolving random graph, or rather an evolving random graph model, an evolving random graph model. And this evolution is in continuous time. It was also before, but the time was from 0 to 1. Is in continuous time. So q is, a number in 0 infinity. And so what is happening here? These uij on page 4, they were, of course, independent. They are IID uniforms, and so are these exponentials. So the family eij over all pairs ij is an IID family. And so finally we have a graph where, okay, so this is more important picture, so I'm drawing it. Here's n, 1 up to n. I'm putting them somewhere on the paper, but really there is no geography here. And so their edges arrive at rate 1. So this is how I would call edges arrive, or rather open edges. So they are open. Open edges arrive at rate 1. There is n vertices, and then at some random exponential time, there is an edge, and then there is waiting time, and so initially there's the time that you wait for the first edge is of course exponential n choose 2. Then you can then you get the first edge, then you have exponential n choose 2 minus 1 rate for the next arrival. But maybe that's not the best way to look at it. But still, there's this waiting times, and basically any pair has its own, any pair of different vertices has its own independent exponential, and okay, this is evolving. And so it's interesting that this is a multiplicative coalescence. So it is a finite, of course, it's a random graph. We did nothing. We just made a time change, but this is a multiplicative coalescent. So multiplicative coalescent. And what do I mean by that? I mean that if you look, okay, so let's look at it here maybe. Here's one connected component. Okay, so for example, this one has 3 vertices, and there is another one. Okay, there is intersection, but please note this is not a true intersection. Edges intersect on the paper, but there is no, connectedness here. And so there is another connected component. Okay, so here. And so here we have 2 connected components. The first one has 3 edges, 3 vertices, 2 edges, but 3 vertices, and the second one has 2 vertices. And there could be, in general, one has X and the other one has Y vertices. And now you ask yourself, at what rate do these connected components connect? So this is, they call coalesce. So there is some coalescing, there is merging of mass. And so the question is, main question to decide, which kind of coalescent it is, at what rate do, of course, it's a Markov process. I mean, the point of introducing these exponentials, sorry for not saying this earlier, is that, now it becomes clearly a Markov process, Markov chain, if you wish, in continuous time. But even the vector of connected component sizes will be a Markov chain, and this is also this is interesting. It's kind of the main point. At what rate? And when I say at what rate, I already implied that there is a Markov property. At what rate do the
Vlada,
yes.
can I ask you? As I understood, still the all number of the vertices is fixed. It is
Yes.
small n.
Yes.
Yeah? It is fixed. Yeah? Okay.
Yes, it's still fixed. So it will soon, change, but it is fixed. So we just have a finite. Each nth model is finite in itself, but soon there will be an extension. But here I'm asking, at what rate do the two does a pair of connected components merge? Okay, I didn't have time. I mean, I didn't have a lot of space to write this, but here I have an example. There is one connected component of 3 vertices, and there is another of 2. And the question is, you could have, a general setting, but here we already see a point. So we know that, I'll tell you the answer, and maybe you already see that the rate.
And what is intensity? Because
sorry?
They may merge in few steps.
Aha. Yes, but okay. So what do I call by merging? Yes, when I say rate, I mean instantaneous rate. Okay, so yes, of course, and everything will merge in a few steps. If you think about it, there will be some finite time at which everybody, sufficient number of edges will happen, and everything will merge together. Okay, so then it stops being interesting from that perspective. But now I'm thinking, somewhere in time, I see, for example, this configuration. It's part of my configuration, and now I'm thinking, what is an instantaneous rate? There is truly an exponential in there. There is a rate at which any given component of size x Vitaly knows the answer since long ago, so but of course he won't say anything. So here I have x vertices and here I have y, and there's an instantaneous rate at which they merge, they coalesce. And by that I mean just there has to be an open edge which connects any one vertex in the first one to any one vertex in the second one. So if there are two connected components which are not connected together, that means there is no such edge. And then there is some instantaneous, okay, just like in the exponential. So here you have exponential with rate 1, and so we see that the model tells us that okay, every pair, for any pair, there is rate 1, any pair of vertices, there is rate 1 of an edge becoming open, so an edge appearing. And of course, the memoryless property of exponentials makes it so that if I see this in my configuration, then the, how do you call it, residual time, right? So I know that certain exponentials did not happen, but the residual time is still exponential. And then, of course, I see I have x times y possibilities. For any vertex in here, I have any vertex in here. And that's a possibility for instantaneous merging, okay? So it will be that it is going to be a multiplicative rate. And that's precisely what a multiplicative coalescent is. So I'll pass to the next piece of paper, giving you more formal definitions. So multiplicative coalescent, it is a process, and now you have to specify the state space, but I kind of don't wish to go into big details here. So it is a process, Markov process of well, let's call it describing, okay, describing mass evolution of blocks with mass. So there are some blocks, and each block has mass in a way that any pair of, just any pair, there cannot be a triple simultaneous merging, so any pair of blocks where one block has mass x, so comma, where one block has mass x and another has, let me put the light on, has mass y, merges, so that where any pair of blocks merges at rate x times y, or maybe that you could have a constant times x, always the same constant x times y. So this is not very precise, but it is, it is giving you, it is truly what is happening here on this finite state space here, and it is more precise than the picture. And there also, so this is one famous coalescent from the mid-90s. There is something also called additive coalescent. And I could write the same definition, and it would be, a Markov process, blah, 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 blocks with mass, and then merges at rate x plus y. Okay, so because it's additive, and then people started at Berkeley, where I was a graduate student at the time. Several professors got very interested, and they started studying general coalescence, not only with such rate and such rate. But it turns out that the only, the only truly the only models, so you could have a much more general rate, and these are very interesting, perhaps more interesting from the perspective of applications than these, but you lose the graphical representation. So there is additive coalescent is linked to branching processes, and multiplicative coalescent is linked to random graphs and also to some branching processes, but additive more so to trees. Okay, so this is random trees and branching, and then there's of course other coalescents which are coalescents without mass, and here you have, so you would have I would call them exchangeable coalescents. So they have good exchangeability properties, but in fact blocks might have mass, but you ignore them. The rate is, for example, if only pairs every pair merges at rate 1. No matter what is the mass of each block, they always merge, and this is called Kingman coalescent, in fact. So this coalescent also existed and is very famous in genetics. Yes, in genetics and applied probability linked to genetics. And so Kingman coalescent existed from the late 70s, and certainly papers, Kingman papers happened in the 80s. But he was talking about his coalescent, the coalescent. This is called the coalescent, and these are multiplicative, additive. So only they have nice interpretation in terms of discrete probability models like graphs, trees, and here's Moran model and so on. The others, they do exist as processes. You can define them on such spaces, but there is they're much harder for the analysis, and there is less of this kind of probabilistic combinatorial connection. Okay, so now all this, what he did, he extended the definition. So what Professor Drogovtsev understood, n should not be finite always, and so the multiplicative coalescent. So it's not a Markov chain; it's now multiplicative coalescent, has a natural state space. And it is striking. So all this extended the definition. You could have now an infinite. So you have infinite, and okay, let me call it. So it is L2 decreasing. Okay, it is L2. So here's here a vector x. Let me turn on the light in the office. So here's a vector x, and it has infinitely many. It's in L2. That's a state of the coalescent. So you have x1, x2, x3, and so on. And this arrow going down to the left, to the right, indicates that they are ordered. So okay, so it is convenient to order the masses. And so what x represents, it's, okay, and of course, some xi square is finite. So x represents a state, a typical state of the multiplicative coalescent. So here, you could, it is just, so now you could write a generator, and, probably, I understand your group is very, does very sophisticated stochastic analysis, and, my work with Vitaly convinced me that, Vitaly writes everything very, very precisely in terms of generators, and it helps in many situations, but, in talks, it may not be the best way, of course I could write it down, It is a Markov process. It has a generator, and you know how. I mean, it's also perhaps a good exercise for you to write its generator. But this is a description.
Vlada,
Yes.
you can do the things as you want, as you prefer. Yeah,
Oh, okay. Yeah. Okay. So I just tell you in words that what happens in this system. So there is, of course, now you see there are infinitely many possibilities for merging, because now there is this process, say xt, and so now it is a random process. Here's the largest component, here's the second largest size. Okay, so these are size of the largest component block, or rather mass. Okay, so this size is truly mass, and this is mass of the second largest, and we keep going, mass of the third largest, and so on. And there are infinitely many blocks, but so what's interesting, they are not in L1. The mass is not finite. It could be finite. The total mass could be finite, but then it's not interesting, because then in finite time everything collapses together, and then you're okay. Okay, it's something. It's like it's a process, but it's not that interesting. It becomes constant after a while, and if it starts from so x is, say, x0 is x0, you could start from a random starting point, but let's not. Okay, so we have a vector in L2 decreasing, and if it, say, this is a starting point, then probability that xt is in L2 is 1. And so for every t, or I could clearly put the t inside. What is interesting, I mean, this is very easy. It also happens if you have finite number of components to start with, and of course this property is it is simply extended if you have infinite amount of blocks. I mean, infinitely many blocks. So there is a quantity that we call S2 or S. So it's the main quantity for the multiplicative coalescent, and that's the square. This is the L2 norm squared of the x. And this is a nice process. I mean, it's a stochastic process in running on the reals, and this property is property about S, and we know that S is increasing. I mean, S is a non-decreasing.
I forget, what are intensities?
Okay. So the intensity, so the rates are the rates are, so here's your, if your state is this x1, x2, okay, then this change, there is instantaneous change, and there are many. So here's some xi, the ith largest, and xj, the jth largest. Say that I is less than j. So then at rate xi times xj, so it is a multiplicative rate, the state of the process will become, okay, it will become something. So this component and this component will be deleted somehow. I mean, they have to be taken out. There will be a new, in the graph, you will have xi and xj. They will merge into xi, into a new component, and that new component will have, yes, maybe I should have said here, merge at rate x times y. I didn't say, into a new component, into a component of mass x plus y. So the mass is preserved. Okay, so here, you know, there's infinitely many possibilities. Okay, so somewhere here there is, yeah, sorry, let me just write, and then, you know,
have infinite number of jumps.
Yes, it has.
Okay.
Yes, it does. It does. But there, you know, since it is in little L2, these infinitely many jumps in any finite interval, they do not damage the fact that S stays finite. And so it is, you know, somehow, okay, we could do a calculation if you wish. You know, I'm using my notation probably. Sorry, you said you believe me.
I believe in this calculation.
Yes.
So
yes. Okay, so we don't do it, or
well, as you wish.
Okay. So the and maybe I don't do it. So for example, Vitaly can, you know, when he talks about at some point he might wish to talk in the seminar about our stuff, and then he can also do this, and you know, because we study related model, and there's some similarities. Okay, so so then this is very interesting. It was kind of the starting point. So what he was interested in was these. So it turns out that there are some natural. So he was interested actually in critical, near critical random graphs. So near critical random graphs. Remember, that's the P and C equals 1 over n. And it turns out that there is, so this is something that people, these combinatorists, there were 4 combinatorists, and one of them was the famous Knuth, and there was some kind of other probabilist combinatorist who gave in 93, there was a paper in honor of Erdosh's, I'm not sure which birthday, maybe 80th birthday, and they wrote a paper, and they discovered that there is a window of, there is kind of a critical transition window. So you will be critical if, in fact, you can add a quantity to this 1 over n. You could add t over n to the 4/3. And this is, I think, also something that intrigued Aldous, that the way how this critical regime, you know, what was behind this. And so so this is something that probably is new. I mean, combinatorics is new. So this t could be any real number. It could be positive or negative, as long as it's fine. It could be 0. So if it's 0, it's truly the critical, you know, function, critical probability of Erdos and Rényi. Now they understood that as you could move from the critical probability of being open. So okay, every edge is open with this probability, but you cannot move arbitrarily. If you move by this amount, where t is any real number, you are kind of also in the critical regime. All again, what I said on page, I guess 2 or maybe 1, no, on page 3. Yes. So critical regime is when the largest component is of size n to the 2/3. The second largest connected component has size n to the 3rd. The kth largest component has that size. And they discovered that that was true. And so this is, okay, so there is something, you know, deeper happening. And that's a famous theorem from this paper of Aldous. He understood that there is a scaling limit, sort of similar to, you know, I mean, just like the functional central limit theorem, but this is a more complicated model than the simple symmetric random walk. So it is a random graph kind of analog of the scaling limit of the central limit theorem. And so he understood that, okay, so How should I write this? Okay, so there is a theorem. All those 96, 97, okay, saying that if I have a random graph, so G and then this is 1 over n plus, say, t over n to the 4/3, okay, and I sample, I draw a random graph from this model. So this is my G, G1 over n plus
Vlada, we cannot hear you.
Okay, I'm back. Sorry, I had a problem. Actually, my computer, the battery was out and I didn't notice. I'm so sorry. Can you hear me?
Yes, now we can see and
Okay, sorry. I'm very sorry. And then I noticed that, yes, okay. I'm thinking that the recording, it was not affected. I'm not sure what was happening for the last, minute or so, but I see that the recording is going on. So it seems that, let me see. Yes, it's okay. So the hour is already over, and I didn't get to the immigration, but I let me then finish with this theorem, and then we can talk some other time about this. If you are happy, I could continue. Vitaly can continue in the meantime about something. At least you learn about multiplicative coalescence and the main result of the famous result that has been after that it has been resurrected in the same way that functional central limit theorem has been resurrected every time people have their nice model and they say, okay, but under diffusive scaling, some natural scaling, my process converges to Brownian motion. And so there are some random graphs which are not as nice as Erdős-Rényi, but they are similar to the Erdős-Rényi, sufficiently similar that there is again this convergence to the multiplicative coalescent, to all the standard multiplicative coalescent. Okay, so I was going to say here we have here this is the the easiest theorem from all this. Then he generalized it in the same paper. He didn't have to draw truly random graph, homogeneous random Erdős-Rényi, but some other graphs. But then never mind. Let's take this. Let's call it Gn over 4, or let me just write it Gnt. So t is this parameter offset here, and it is distributed according to this. And then you write down the component sizes. So let x1 nt, x2 nt, and so on. Well, they go until some place, and then you insist that it's an infinite vector, so you put 0, 0, 0. So there's going to be finite. So GNT is a finite graph. It has n vertices. There will be finitely many components with non-trivial mass, and then you add zeros afterwards. So you pretend that this is an infinite vector in L2 decreasing. And so you have this, and you are guessing here. I'm going to write it is the size of the largest connected component of G and T. And so xj, so this is the size of the second largest connected component, and so on. And it turns out that this converges in distribution, but not quite that. Of course, there has to be the scaling. Remember, page 3 said that the largest component is of order n to the 2/3. The second largest is of order n to the 2/3. They didn't quite know that they would be, there would be a limit, but Aldous proved that there is a limit. So we let's scale by n to the 2/3. So we put these largest masses, but then we scale each of the coordinate by n to the 2/3. Okay. Then there is convergence in distribution to x star t. There's a process, in fact. So this is x1 star. It's a vector valued, x1 star t, x2 star t, so on, so for each fixed t, where t is this offset, these converge in distribution with respect to the metric defined by the norm on L2. They converge to this x star t, where x star as a process exists. Actually, it's not a process, it's an entrance law. Okay, there is something, it's like a Markov process, but it exists on all of R. It is defined for any real number, but it starts from a state which is not in L2. So there is no Markovian way to get to any point, to get to the state at time t from the state at time minus infinity. You cannot define the starting state, but still it evolves as a Markov process from any finite time, any given time onwards. So x star t is an entrance law, of the multiplicative coalescent. It behaves, in other words, x star t, and it is a specific entrance law. It Aldous specified it. X star t when t is bigger than any z, z in R, is a multiplicative coalescent. Started from its random, initial state, x star of z. Okay, so you just know what is its starting law, and then from that time on, it is a multiplicative coalescent. It is because x star z will be with probability 1 an L2 vector, and from then on, it is a multiplicative coalescent. But in fact, you know, as you move t going to zero, t going to infinity, so as t, going down to minus infinity, as t decreases to minus infinity, x star, well, the norm of x star t is going to 0. And of course, if the coalescent were to start from 0, it would be just 0. Zero masses don't do anything. So it's somehow, it's an entrance law. It starts from dust. Starts from dust. At minus infinity. And of course, as t goes to plus infinity, then these, you know, the L2 norm goes to infinity. So there is a, you know, giant component appears in the end. Giant component appears at infinity. So it is somehow all this interpreted really well, very precisely, this transition window. So the phase transition window, when t, this parameter t, sort of the second order, you know, approximation to this 1/n, as t goes from minus infinity to plus infinity, how is the component sizes, how are they changing, or at least, yes, okay, you have this very precise weak limit to this process. And okay, one more thing that I can tell you, and you know, then we end for today, and sorry about being late or being long. So I didn't tell you how you specify this law. Okay, so you need to know how at any time z, how you would start. You know, what is the starting point for the entrance law? Okay, so there is a characterization of x star. So x star is, by the way, let's name it. So this is what is in the literature. So not double star. So this is called the standard Aldous. I always put Aldous multiplicative coalescent. There is the standard eternal. Okay, some people say eternal because it's, you know, it is the entrance law, and it is specified by the law of x star t equals, so that's interesting, and I could tell you at another time why this is so, and I was hoping to tell you, but there's so much to tell. So this distribution of x star, or let's call z, okay, so it's some other z, so any z or t, so you have your time, and so how is this Markov process and entrance law characterized? So this is distributed as the ordered excursion sizes, excursion lengths of okay. Now you have a Brownian motion, so there is an auxiliary process. So let's call so this, here's a digression. W is a Brownian motion, a standard Brownian motion, and then it is running in time. You know, you have Ws. There is an auxiliary time. Ws is bigger than 0. Then you form a process. Let's call it Y of S. Then you take Ws plus Ts, Z. There is this Z. Zs minus 1/2 S squared. So there is a drift, this inhomogeneous drift, I think, you know, Z minus S. And okay, the infinitesimal drift, and then you have this process. So it's a Brownian motion plus a parabola. And then what x star z, okay, now there is a reflected. So usually he called it B, I mean, with some notation. So BS is reflected Y above past minimum. So this is Y of S minus infimum U less or equal to S, Y of U. So this is Y reflected above its past minimum, infima or minima. It is Y is a continuous process, so it is the same. Okay, so this is a digression, and now X star Z are the ordered excursion lengths of Y of B. Okay, B above 0, from 0. Okay, let's draw a graph. Maybe, I mean, draw some graphs. So, okay, I need a new, just one more page. Okay, there is so there is W. W is a Brownian motion, but you have this. If Z is, well, some number, Z is, let's say, bigger than 0, but it's going to be the same. So you have Brownian motion, okay, I don't know, nobody knows how to write it, and then you have, I mean, draw it, but we all do draw it, we try, and then you have, there is a parabola, there is something like that, and so there is Brownian motion evolving around this parabola, and then here it goes down and down and down, because parabola is rather, it is strong, stronger than Brownian motion, but it could, okay. And now what's happening, now you try to, you bring it above past minima. So this would be a graph of Y, okay? This would be a graph of Y. Now graph of B is when you draw above past minima, that just means, so you see B as a process, it's always non-negative. So there are these excursions that happen, okay, above past minima. There's something, okay, a Brownian-like, and it turns out that the excursions, so here there is only countably many excursions. You can find the largest, the second largest, and so on, the third largest, and so on. And when you put their lengths in, you order them. So you may not order them; they are ordered in some natural way in terms of this parameter S. So this is auxiliary time S. When you order them, then you get an L2 vector, and this L2 vector is specifying the same as the law of the standard. I mean, the law of the standard multiplicative coalescent at time Z is equal to the law of the excursions, excursion lengths when they are reordered. Here they appear in some other interesting way that I could at some point try to explain why it is so, but okay. And immigration, let's leave it for now. Okay, so at least here's the multiplicative coalescent without immigration, and you understood that there are some interesting links, I hope, from the combinatorics to the stochastic analysis. Okay, sorry for extending. Yeah, I think it's good place to stop. 10.
Vlada, thank you very much for very interesting introduction, and in my opinion, it is definitely not the last talk of you.
I'm glad.
It was very interesting, and maybe somebody have a question. Please.
Vlada, what are the methods of proving? Is it relevant techniques or some or do you study generators of that processes?
Okay, that's a good point. So yes, generators are valuable in his analysis, but okay, so Aldous is not a generator, expert on generators, but he likes martingales. And so, of course, generators are linked to martingales. So in fact, the method of proof in this result, so that's an interesting question. The method of proof is to interpret. There is a way, so this is something that I could have told you today, but I decided not to. In some sense, you know, I took a path that I wanted to explain how did this study came about, what is the history of it. But now the actual Aldous' approach was to embed. So he constructed the coupling and of course did some martingale analysis. So when you say generators, there is a natural connection to the martingale, and he uses martingale in his analysis. So he actually could reinterpret. So let me just find the what is converging to what. Okay, so here's the object. So this object, so this is a pre-limit setting. Okay, we have a finite graph. We just look at this at probability in the near critical regime. This is some near critical regime, and so he could find the idea was to find a way of describing, actually embedding or coupling. Okay, so he found a way to couple the component sizes inside of a random walk, and not quite random walk, a process which is similar to a random walk. He calls these, I think, so what is the depth first? Yes, so there is this breadth first search. So breadth. So there's some combinatorial tools, breadth first search for, when you look at a graph, you want to find connected components, and there's a way how computer would do it. So a human would just have a look, and somehow they would do their algorithm, but the computer might wish to do a search, and there is something that is called in computer science a breadth first search, where you start from one component, then you look at the children, then the children over the children. I mean, you have to define this in a way. There is also depth first search. So, but here he took this algorithm, and then from there he went to breadth first walk. So he called them breadth first random walks, and they are not quite random walks, but they're sufficiently similar to random walks that he could analyze them, and he could prove that under certain rescalings, these breadth first walks actually converge to Y. Okay, just like a simple symmetric random walk converges to W, then these breadth first walk, they are a little bit weird, they converge to Y, and the coupling is so that the component sizes of this graph are actually they are linked to the breadth first walks. The walk does something, so it's like a walk, walk path, and it has its excursions above past minima, and the component sizes of the random graph are its excursions above past minima. So now I'm drawing a walk. You can draw a walk. Brownian motion is hard, but okay, it's bad. So already there is a coupling of component sizes here to the excursions lengths of the breadth first walks. Okay, now if the walks converge to the process Y sufficiently strongly, then the excursions, or rather excursion lengths, will converge in a good way to the excursions of this, and that's that's the main idea. So he used this kind of that's the idea of his analysis, and then he uses martingales, and in that way the generator of the multiplicative coalescent to achieve, to have his good estimates on the rates of convergence. I hope this answers your question.
Yeah, thank you very much.
Thank you. Another questions, please. Vlada, I have a question relatively to the random graph model, Radioshiny model. Actually, you said several times and insisted that there are no geometry. This is only about the connected components story.
Yes.
But for me, because I'm interested in some model of moving surfaces, moving lines, and so on, it would be interesting to have some geometry. So, do you know there are some results? Are there some results about the evolution of the random graph where the geometry is involved? For example, estimation of the time when the graph becomes not to be planar graph or something like this.
Yes, okay. I'm sure that certain things, yeah, so this is something that I would, okay, so I don't know from the top of my head. It's a very good question. I would suggest that, so there is this, I said famous paper, so I think it's Jansson, who else was there? There was Knut. There was I think Pitel, and someone else, and it's called The Birth of the Giant Component. Okay, so it is about the giant component, but and it is 1993, but it has, I would start searching, who is citing them, because it's somehow, it is kind of a masterpiece, and they do mention various results and improve on, various results about, okay, I don't know if you would call it geometric, but, whether you can find, at which times you can find triangles, or so cycles, triangles, or positive density of triangles in the graph, things like that. So combinatorial features that are present. Spencer, I would call, yeah, so probably Spencer. Now I remember it. Yeah, so these four authors. And I would, if I were, I mean, I would try to see who is citing them. Well, maybe some people do things and do not cite them, but, if something like that was done recently, I would first go to check what is in their paper, what they, say about various features of this random graph. And then, because, I mean, in some sense, this is because there is no geographic space, then, okay, there is a priori, geometry is not interesting, but there is combinatorics. So who is interested? I mean, there is about the combinatorics in the sense you care if they about connectivity. 3 connectivity, 4 connectivity, and so on. So they list some results in this respect, and then there might be other people who are studying similar models, but yeah, I don't know, on top of my head, it's not part of the, yeah. So this world, what I was giving you the introduction to the mid 90s, and everything that came out of this since, I mean, that is linked to this Aldous breakthrough, is about multiplicative. I mean, it is about connected component sizes and no geometry a priori. But there are some models that are geometric kind of graphs. They are not, I mean, okay, they're not homogeneous, and they're not completely homogeneous. So what is, in the pure random graph model, every vertex is the same, being connected is, you know, to any other is with equal probability. And then actually to advertise our work with Vitali, we study a class of graphs that are not homogeneous. And many other people in the meantime studied various graphs that are not homogeneous. And for example, I would also have a look in Bolobash, so Bolobash and Riordan. Bolobash, Riordan, they wrote several papers, Riordan. And they collaborate also with Janssen, possibly with Spencer at some point, but they have been studying inhomogeneous random graphs. So there is a priori some structure in their model, and then they studied the phase transition. And if the graph, you know, somehow, I think you might be disappointed because, but still have a look, because in their work the graphs are inhomogeneous, and then in many cases the inhomogeneity is not strong enough so that when they pass to the limit they still see the multiplicative coalescent. So it is somehow, you know, in the, I mean, okay, it is sort of, you know, like it is the way how many processes, they are not simple symmetric random walks, but actually they are not so far away when you pass the diffusive limit. So so in that sense, but maybe, you know, I can have a look if you wish. I can try, or maybe you could write me.
Yes, surely. Okay, I will do. Also, from the technical point of view, let me comment that in study of the Kinman coalescence and exchangeable things, the dual processes are very helpful.
Yes.
And they involved exactly martingale approach. Yeah, maybe in this theory the same happen. Yeah.
Yes, that's a very good point. And somehow you see, okay, so and somehow the dual process. So I also, so when I said in the meantime, you know, I have been working on exchangeable coalescence also for some time. And I understand what you mean. And there, the dual property is also kind of linked to a certain, it's a way of reversing time. There is something in the background that is, I mean, it truly, you know, there is a process that could run and runs in reverse time. Now, multiplicative regime is not good for that. There is no way of reversing time in a nice manner so that you see, you know, you can go backward. But actually additive, so the third case that I said was amenable to the analysis, the random trees, yes, here you could reverse time. So there is truly duality also helps you because it's about masses of trees. So you have like these continuum trees. That's also, you know, Aldous is very famous for that. So the continuum trees, which are being in forward time, they start merging, but actually there is a duality in the reverse time. They are being cut. So there are certain cut points, and the tree is breaks into two or maybe three, two. Yeah, so it's truly, you know, at typical points where the trees are being dissected. So here you have duality in the sense that there is a process that you can define in reverse time, and it actually helps your analysis. It is better to study trees which are being split into forests, and then this forest is split further and further and further, and it could be continuum forests that are split. And here you have duality. Yes, exactly. These are dual processes to some kind of how do you call this, measure value diffusions in and, you know, from the right. And here you kind of, you don't have that, but at least in forward time you have a lot of good. So the process running in forward time is quite amenable to to the analysis. So there is plenty of martingales. The generator is nice, and you can, I told you about this S2. So the L2 norm, but actually the L3 norm and the logarithm. So the ratios of these L3 norm and L2, and you can actually work out quite a bit from just knowing that any two components merge according to the multiplicative rate. It is something very nice, and you can feel it sort of, because you see, if you have powers, then the rate will just create some other powers. So yeah, it is still okay, and this will be like polynomial. I mean, truly, you have a norm of size 3. I mean, you have a L3 norm. You won't exit from this kind of polynomial thing. But now, if I were to put some alphas that could be even more interesting from the application perspective, some really odd positive number. Oh yes, okay. So now the generator is not so nice, and you somehow, yeah, okay. I mean, there's much fewer, many. How do you say? The number of results which were done about these more general kind of rates where there is a multiplication or addition. You could put alphas also here, and you could create more and more structure. So this is really, I mean, these are really hard papers that have been written, and there are many open questions that seem silly, but they're still open. They have been known for these exchangeable additive multiplicative since 80s or 90s, but here we don't know. I mean, people don't know, and many people gave up, but maybe they shouldn't have. But simply, okay, there is a order of magnitude of difficulty when you go to these, yeah, more general rates.
Thank you very much. So actually, before this pandemic, it was a very good habit to have a dinner after seminar and to eat and drink something. Now, unfortunately, we cannot do this, so I only can to express my gratitude for this nice talk, and
yeah, thank you very much. Okay, let me put. Sorry.
Success with Vitaly collaboration,
Yes.
and hope to see you again at our seminar.
Yes, thank you very much. I put my camera on. Let me see if I, yes, just to express my gratitude, and thank you for bearing with me. With all the technical difficulties, we still managed to I still told you enough of material, and I hope you benefited. I'm glad that you accept my somewhat informal style, but it's good. It's part of the multicultural world, and we should
Yeah.
Thank you for being tolerant. Yeah, exactly. Okay. So let's keep in touch, and yes,
Sure.
and keep up the good work, and yeah.
Bye, and bye everybody. See you next week. Bye.
Bye bye.
Goodbye. Thank you for nice talk.
Goodbye.
Thank you. You're welcome, and I'll send you the link to the recording. Okay. Bye bye.